In the early days of amateur radio, new operators started off with a crystal oscillator which has high frequency stability. But a crystal oscillator cannot cover the entire amateur radio band. Variable frequency oscillators permit you to work the entire band. Yet, the problem of frequency stability has to be taken care of. In the olden days, when most radio amateurs were using homebrew equipment, a little bit of drift was usual. Other operators did not bother much about it. But now, with modern commercial radios having high stability, frequency drift is a real problem. I have often heard someone telling the other person that you are off frequency by 50 Hz on 7 MHz band. Modern radios have very narrow pass bands as they have good filters. Hence, it is easy to detect even small change in frequency. Calibration of commercial radios are accurate to the fraction of a hertz. Conventional variable frequency oscillators have their frequency controlled by a tuned circuit. A tuned circuit in a VFO typically contains an inductor coil and a variable capacitor, popularly known as gang capacitor. You may have seen double gang capacitors in old radios. They have a set of fixed plates known as stators and movable plates known as rotors. When the rotors slide in between the stators, capacity increases. Capacity decreases when the rotors move out of the stators. Two sets of rotors are mechanically linked in double gang capacitors so that capacitance in both sets can be varied simultaneously. For a simple variable frequency oscillator, a single gang capacitor may be enough to control the frequency. As mentioned initially, frequency stability is the most important problem with conventional VFOs. Frequency drift is more at higher frequencies than at lower frequencies. One simple solution was to build a low frequency VFO and up-convert to a higher frequency with a high frequency crystal oscillator with good stability. The resulting output will have both the sum and difference of the two frequencies by the heterodyne principle. Desired frequency is selected using a bandpass filter and then amplified to give a stable high frequency signal. Another option to stabilize a VFO signal is to use junction field effect transistors, JFETs, instead of conventional junction transistors like NPN or PNP. Characteristics of PN junctions in junction transistors vary with change in temperature. Hence, VFOs using junction transistors drift much more than those made with JFETs. In JFET, the main current from drain to source does not pass through any PN junctions. The good old due to VW and QRP, which I made in late 1980s, had a VFO using two BFW10 JFETs. A stable, well-regulated power supply also improves frequency stability of VFO. Enclosing the VFO in a separate, sturdy metal enclosure can reduce frequency drift. The VFO of our VU2 VW and QRP had a separate metal enclosure. A novel concept for constructing a stable VFO is to use varactors instead of mechanical variable capacitors. Mechanical and thermal stability of varactors is better than that of mechanical variable capacitors. Varactors are silicon diodes biased with a direct current voltage. Their capacitance does not change much with temperature variations and mechanical vibrations. A disadvantage of the varactor is the non-linear variation of capacitance. This results in lower end of frequencies being compressed on the dial, while high frequency end will be wide. It is possible to tide over this by using non-linear potentiometers. When I inquired at a local electronics spare shop, logarithmic potentiometers were not available. Only linear potentiometers were available. In this digital era, modern radios have DDS VFO, which stands for Direct Digital Synthesizer Variable Frequency Oscillator. DDS VFO has much higher stability. They are smaller and have no moving parts. It is easy to control frequency with a digital computer. That is how we have Computer Assisted Transceiver Control or CAT control. As we go higher up in frequency, we need a GPS disciplined oscillator, GPS-DO, for good frequency stability. GPS-DO, also known as GPS clock, is a combination of a global positioning system receiver and a high-quality stable oscillator. Signals broadcast by GPS or other global navigation satellite system satellites is used to control the output of GPS-DO. Most commercial radios have two VFOs, VFO A and B. There are some which even have 4 VFOs so that each can be tuned to a different frequency. They can be used for split operations with transmit on one frequency and receive on another frequency. In my IC2730A radio, a full duplex radio, one VFO can monitor when the other one is transmitting. That is possible only if they are set to different bands. If both are set to the same band, the receive VFO will be muted when the other VFO is used for transmission. Otherwise, the transmitted signal will overload the receive VFO.